biology. This is your second flip lecture. It's on the nature of science. How do scientists do science? Before we get started, let's quickly talk about who a scientist is and how they think. So let me read this to you. People who think like scientists don't accept everything without question. They need evidence, understand that knowledge is important, have a sense of wonder and curiosity, drive real progress, and seek truth, are not afraid to think hard. So today we're going to be talking about how scientists actually go about doing science and what we consider science. Let's first start off with how simple ideas lead to scientific discoveries. You might recognize this guy from Mythbusters. I'm just going to play you his introduction, and I will post a link to this whole video on Haiku. Turn that up for you guys.
One of the funny things about owning a brain is that you have no control over the things that it gathers and holds on to, the facts and the stories. And as you get older, it only gets worse. Things stick around for years sometimes before you understand why you're interested in them, before you understand their import to you. Here's 3 of mine.
So if you're interested in finding out the things that are important to him and the scientific discoveries that help him as he moves through his career and the things he's interested in, you're going to click on this link. He also talks about how simple curiosities lead to actual big discoveries. So we're going to continue on with how scientists do science. Let's talk about the methods that scientists use to investigate. I'm actually going to start to the right where it says the scientific method. What you have heard about the scientific method is it is the way to do science, which is actually inaccurate. The scientific method is one method or one way that one or two types of scientists might use. It's more of the traditional method, and even the way it's presented and the way you've heard about it is not necessarily accurate. So the way it's been presented to you is that first you're going to ask a question, or you might have a problem. You might do some background research. Then you will construct a hypothesis. Then you'll test your hypothesis. Then you'll analyze and draw a conclusion or come up with what you think it all means. And then you'll report your results and decide, was your hypothesis correct or not? This is what we've been taught in school, including myself, and it's not necessarily linear or in one direction and step 1, step 2, step 3. So we're going to call this out for this, and we're going to look towards the left, which is a diagram to describe the scientific processes. You guys will actually be working with this document, and you'll get your own copy, but it's a brief visual to show how a scientist might go about exploring and discovering. So we'll come back to this in just a moment. Before we talk about this, I just want to give you a quick introduction into why I'm saying the scientific method isn't our best way to understand how scientists do science. Here we go.
The scientific method sucks. Now, by that, I don't mean that science sucks. As a physicist, I believe that science has had countless benefits for humanity. But when I was in 8th grade, I learned about this thing called the scientific method. And since then, I have done science, I have worked with other scientists, and I've taught science to college students, to K through 12 teachers, and to 7th and 8th graders, middle schoolers. And from these experiences, I've come to the conclusion that the scientific method sucks. If it's been a while for you, as it has been for me since middle school, let me run through it real quick for you. First of all, step 1, identify a problem. Step 2, do some research. Step 3, form a hypothesis. Step 4, do an experiment with some independent and dependent variables to test your hypothesis. Step 5, analyze data. Step 6, draw a conclusion. It sounds good, right? It certainly matches what we see on TV and in movies and what we see on the news. Unfortunately, it completely misrepresents what scientists do and what science is all about. And this manifests in 4 main ways. First of all, it's incredibly linear. We start with a problem statement and we end with a conclusion. This implies that science is something that's once and done, fixed for all time. Secondly, it's not very intuitive. How do I choose a problem? What do I do with my conclusion when I'm done? If I have no idea what should or even could happen, how do I come up with a hypothesis? This makes the process intimidating and dangerous. 3, there's a focus on conclusion, reaching the conclusion, on getting a fact. Well, what happens when the information changes? What happens when facts change? How does this process capture that? And finally, the focus on experimentation. Now, don't get me wrong. I'm a big fan of teaching students to control for whatever random variables they can. But there's been a lot of really good science that's been done without being able to control for, well, anything. For a moment, I'd like for you to imagine what budget it would take to create a laboratory here on Earth to study the interior of Jupiter, or to form a star from scratch, or to study a galaxy's development. Do you want your tax dollars to go toward that?
So in this, Mr. Cook is talking about his reasons why he thinks that the scientific method doesn't work, and I would actually agree. So although it is one way that we've been presented that scientists do science, it doesn't fit for every single scientist. In fact, it doesn't fit for most scientists. So we're going to talk about a better way to understand this idea. So going back to this, remember, we're not going to talk about the scientific method. He said it was linear, step by step. It can be confusing. It's not really wrong all the way. It's just not the best way to show the process. And the reason is because it's actually more of a cycle. It's actually more fluid. So there's a little more wiggle room. You don't have to do this step and then do this step. There's a lot of moving parts to it. So if you look at the diagram to the left, you'll see that there is a section on, sorry, my husband's texting me. There's a section on exploration and discovery. There's a section on gathering data, interpreting data. There's a section on testing ideas, benefits and outcomes, and community analysis and feedback. And there's Miss Kuka. So we are going to be working with these scientific processes. Please don't memorize them. We're going to be working with them. I just want you to know that scientists use all of these different processes, and it's really important that you know that there are many processes involved in these scientific methods or scientific processes. So you'll hear the term scientific processes used in my classroom this year. Ms. Kuka will probably use the same, although we will mention this idea of scientific method and the reasons why we want you to look at it in a more, in a different way that you have been learned or been taught before. So let's talk about what is the difference between a law and a theory and a hypothesis. So if we look at this diagram, there's a bunch of parts to it. We are going to start onto the left, and we're going to start with observations, which you should have made during both the email lab, and you should have made them during the How Many Drops lab. So when we're looking at observations, we're looking at different types of data. Qualitative, meaning that you're going to actually describe what you see. You did that in your How Many Drops lab. You might have done that in your email lab. And we're looking at quantitative data, like when you counted the drops. How many of something? That's what that would answer. You might also look at existing knowledge or other people's observations that have already been made. Then, once you make observations, you can make a hypothesis. It might be a testable explanation or a prediction. Then you might move to the experimental process. You might learn some things, come up with some conclusions based on your observations or data, and you might revise. So it's cyclical. You might use those experiments to build on them. And in science, we might develop a theory which would have to be tested again, and you might revise it or it might strengthen. Let's talk about what a theory is. So if you look at the top right, it says a theory is a hypothesis supported by many experiments. I'm going to clarify this in just a second. And it also talks about a scientific law that they're facts of nature accepted as truth. So let's move on. In the picture at your left, it's describing these differences between a hypothesis, a theory, and a law. So a hypothesis is a possible answer to a question, or if you read the blue box, I said that a hypothesis is a testable explanation, an idea, or a prediction. A theory, in the picture to your left, we have a guy that's dropping an apple, right? It says a hypothesis has been tested and supported many times. Theories serve as a basis for describing patterns that we observe in nature. I'm telling you a theory is supported by a large body of scientific evidence. It actually explains how nature works. So in the picture to the left, we have the hypothesis was, oh, I think an apple's being dropped on my head by this. The theory actually should explain how that happened. How did the apple drop? And typically it is non-mathematical, but not always. A law, if I'm looking at the picture to the left, we have this guy in a parachute. He's talking about gravity. It's a general statement that describes a pattern in nature. I'm saying something similar. A law describes what nature does under certain circumstances, and it can be and is most often mathematical. So I'm going to give you a quick introduction into this. I'm only going to play part of this video, but again, I will link this video and all videos on Haiku. Here we go. If I can get it to play.
We need to get something straight. Evolution by natural selection is a theory. So is climate change. But people keep saying that like it's a bad thing. I get it. I understand your frustration. We're all searching for ultimate #truth, and complex, challenging ideas don't always fit nice and neatly in our brains. But what is truth? Are there different levels of truth? Are some truths truthier than others? Well, I don't know, but I do know this. Science is the absolute best tool we have for understanding how the universe works, and theory is not a four-letter word. If we're going to trust science together, the least we can do is speak the same language. Words like fact, theory, hypothesis, and law mean something totally different to a scientist than the way they're used in everyday speech. So let's get them straight. Facts are really just observations about the world around us, and we observe things every day, like that it's bright outside when I look out the window. And we often develop explanations for those observations, like, okay, the sun is probably up. Congrats! We just developed a hypothesis. But a hypothesis isn't something you prove. It's something you test. So, let's walk outside. It's bright, the sun is up, hypothesis confirmed. Way to go! We did a science. We often come up with multiple hypotheses to explain an observation. We just eliminate the ones that are wrong. What's left over is not a theory or a law or an ultimate truth. It's just a possible explanation for something, one that can lead us to new hypotheses, which may agree or disagree with the original one. It's a never-ending story, only without the big fluffy dragons.
That's so good.
All right, so in this video, It's Okay to Be Smart is the YouTube channel. He's going to continue to talk about the differences between a fact versus a theory versus a hypothesis. You have a section in your notes that you need to describe these things. So make sure that you go to this video or this video to check this out. I will post both of these links, the one that we just watched and the what's the difference between a scientific law and theory. This is a TED Ed video. Both of these links will be posted on Haiku, where you can watch them in more detail. So to sum up your notes, Since most of it is actually done by you watching those videos, if you haven't watched them, you're going to go back. I'm asking you to, in your own words, meaning that I don't want you to copy the words from the video, I want you to develop your own understanding. I'd like you to write a paragraph describing what scientists do. Make sure that you use your notes to help you explain, and at the bottom of your notes there's a checklist that asks you if you mention certain details in your paragraph. Please make sure you check that out, and if you want to get an idea before you start writing, you can watch this video to your left. It's an Adele parody, but it's pretty funny. It's that Mr. McFadden, that teacher that you watched earlier in the Nature of Science unit. So, all right, good luck on your notes. Please ask for help. Make sure that your notes are thorough enough for you and to be usable on a quiz. Good luck.